Welcome to Math 201. This is our first part of lesson 4.6 related rates. Today we learn how to solve problems where several variables are changing at the same time. And these kinds of problems are called related rates problems. We'll start with an example. Water is flowing into a cone. This cone has a height of 16 centimeters and a radius at the top of 4 centimeters at a rate of 2 cubic centimeters per minute. How fast is the water level rising when the water is 10 centimeters deep? So I'm going to start by drawing a cone. Okay, I'm going to label it with the dimensions they gave me. The height of the cone is 16 centimeters. Okay, and then the radius at the top of the cone is 4 centimeters. Okay, and we're pouring water into this cone. So let me use blue here for water. And water is pouring in. So the water is at some level. This level is changing. So I'm going to call the height of the water H because that is changing, right? We're pouring water in here. So the water's at some height and it's going up. Okay. And then the radius is also changing because as the water level gets higher, the radius is also getting bigger. And Um, what I know about this radius, you might notice that the height and the radius have a relationship in that the radius is 1/4 the whole height. The radius at the top is a quarter of the whole height. That relationship holds in the cone due to similar triangles. Okay, so a little bit of high school geometry reminder, but this radius right here is going to be h over 4. Okay, because this radius is a quarter of this height, this radius is a quarter of this height. Okay, so we've got a picture where we have labeled the things that are fixed with numbers. So 16 and 4, these numbers are fixed. They are not changing. It's the height of the cone and the radius at the top of the cone. And then things that are changing, we labeled with letters. So the height of the water is changing because this water is filling up the cone. And the radius of the water level is also changing. So that also is labeled with a variable. Now, I just want to write down what do I know and what do I want to know. So what do we know and what do we want? Okay, so I know, other than what I've put in the picture, I know the rate at which the water is flowing into the cone. Okay, the water is flowing into the cone at 2 cubic centimeters per minute. So this is a rate, and cubic centimeters is a volume, right? So this they're telling me a the rate of change of the volume of of the water in the cone. All right, so if V is the volume, then how could I represent the rate of change of the volume? Well, we've been studying a concept all semester of how we represent a rate of change, and that is the derivative. So I know that dV dt, that's the rate of change of the volume of the water, is 2 cubic centimeters per minute. And then what do I want? I want to know how fast, that is the rate at which the water level is rising when the water is 10 centimeters deep. So the water level is being measured by H here, but I would like to know how fast H is changing. That's the derivative dH dt. So I want to know dH dt when H is 10 centimeters, when the water is 10 centimeters deep. So now I have drawn a picture. I've identified what's fixed and what's changing. I wrote down what I know and what I want to know. The next step is that I want to write an equation that relates the variables v and h. Okay, I need an equation that relates the things I know and the things I want to know. So I'm going to write an equation that relates v and h. Okay, and that is the formula for the volume of a cone. Okay, so the volume of a cone is 1/3 pi r squared h. Okay, so I have an equation that relates v and h, but it's got too many variables in it. It's got an r and an h, and I would like to have only one variable. So I'm going to use the fact that the radius is actually h/4. So I'm going to have volume equals 1/3 pi times h/4 squared h. And simplify, and I get 1/3 pi h squared over 16. So, and then times an h. So I'm going to have pi over 48 h cubed. All right, so now I have a nice simple formula. V equals pi over 48 h cubed. A nice equation that relates the variables I know something about and the variables I want to know something about. Okay. The problem is what I know and what I want to know are rates. I don't know something about V, I know something about dV dt. And I don't know something about H. I don't want to know H, I want to know dH dt. And there are no rates in this equation. So I want to introduce some rates into this equation, and I do that by taking d dt of both sides. So I have d dt of V equals d dt of pi over 48 h cubed. So this might remind you of implicit differentiation, which we did earlier in the semester. Um, that is not a coincidence. This is implicit differentiation. Um, so v is a function of t and h is a function of t. So when I take d dt of both sides, I have to remember to use the chain rule. So d dt of v is dv dt. And d dt of pi over 48 h cubed, I'm going to do the power rule. So I'm going to get pi over 48 times 3h squared. But then I have to also multiply by the derivative of the stuff because h is a function of time. So I have to also multiply by dH dt. Okay, now I have an equation that relates the rate I know to the rate I want to know. And now I can start plugging in some things. Only after implicitly differentiating, plug in what you know and solve for what you want. So the things I knew that dv dt was 2, and I want to know what dH dt is when h is 10. DHTT is what I want to know, so I'm going to leave it in there so that I can solve for it. So let's see, I have 2 equals 300 pi over 48. I actually can reduce that. That's 16. So 100 pi over 16, which can also reduce again. That would be 50 pi over 8, 25 pi over 4 times dH dt. And then to solve for dH dt, I'm just going to multiply both sides by 4 over 25 pi. So dH dt equals 2 times 4 over 25 pi, which is 8 over 25 pi. Okay, and my units, this is the rate of change on the height. So this should be centimeters per time unit, which was minutes. So I have a handout called the Related Rates Guidelines. I will also post this as a standalone sheet that you can print out from Moodle. It's also in our lesson here. So we have guidelines for related rates problems. There on the left are some general guidelines, sort of a general how-to for any problem. And then on the right is a specific example. So a related rates problem is one where you're trying to find a rate of change, and the situation involves different rates of change that are related to each other. For example, you might have a 6-meter ladder leaning against a wall, and its bottom is being pulled away from the wall at a constant half meter per second. So we've got a rate. How fast is the ladder top sliding when it reaches 5 meters up the wall? That is also a rate that I'm looking for. So step one is to read the problem. As with all problem solving, spend some time understanding what's really being said and asked for. And then think about what you think, right? So my intuition says that the ladder will initially fall slowly and then fall faster and faster as the bottom is pulled further away, because as when the ladder is real close, the wall is providing a lot of support, and so there's a large amount of force counteracting the gravity of the being pulled down on the ladder as the ladder slides away. But as the ladder gets further and further away, the base of the ladder gets further and further away from the wall is providing less force to keep the top from falling, so the top is falling faster and faster. Okay. Number two, carefully define the variables in the problem. These are calculus problems, and so they're dynamic. Some of the values in the problem are changing and some are static. Be clear on which quantities are which. Okay. So in this example, we need to let x be the distance between the bottom of the ladder and the wall, and y will be the distance between the top of the ladder and the floor. So if I wanted to draw a picture of it, I've got a ladder leaning against the wall. We are letting X be the distance between the bottom of the ladder and the wall, and Y being the distance from the top of the ladder to the floor. Okay. These distances are changing because I'm pulling on the base of the ladder and I'm moving it away. Okay. And the top of the ladder is going to fall as this moves away. Now, the length of the ladder is constant. This length doesn't change. That is always 6 meters. Now, even though the moment in time that I'm interested in is when the top of the ladder is 5 meters from the wall, I'm is 5 meters up the wall, I'm not going to label this with a 5 because this is a changing quantity. Okay, so I'm going to keep it a Y. I'm going to save that 5 in my back pocket for later. Okay, so I just did this part where we draw a diagram. We've got our ladder leaning up against a wall. The distance to the top of the ladder is y, the distance to the bottom of the ladder is x. The ladder is 6 feet. And finally, we want to determine and symbolize what rates are given to you. What do you know? Okay, so they told us that the bottom of the ladder is being pulled away from the wall at a constant half meter per second. So I could symbolize that as dx dt. It's the rate of change that x is moving. So dx dt is a half meter per second. Okay, and then I want to determine and symbolize what rate I want to know. And that is the rate at which the top of the ladder is falling. So that's the rate that this distance y is changing, or dy dt. Step six, you want to find an equation that relates the important variables, the ones we know something about and the ones we want to know something about, x and y. So when I use my picture, I could say, oh, Pythagorean theorem could relate those. X squared plus y squared equals 6 squared. Next, you implicit differentiate implicitly with respect to the independent variable, which is usually time. So you take d dt of both sides of your equation. In this case, we get 2x dx dt plus 2y dy dt equals 0. You just have to remember we're implicitly differentiating, which means chain rule. And then finally, in the very last step, you redraw the picture, this time for the specific constant situation, and find all the values at that moment in time. So the question I'm being asked about is when the ladder is 5 meters from the ground. The top of the ladder is 5 meters from the ground. So I can put a 5 here now. I can solve for this distance and using the Pythagorean theorem, and I get about 3.3. Now plug in all the values that you know, and we're going to solve for the rate that we want. So I plugged in x and dx dt and y, and I'm solving for dy dt. Okay, we solve for dy dt and we get negative 0.33 about. Negative makes sense because the ladder is falling. The top of the ladder is coming down, so the distance y is decreasing. So dy dt should be negative. Okay, now we have an activity. It's a bird, it's a plane. So pause the video, work through these problems, press play when you're ready to see me go over them. With your binoculars, you watch as the space shuttle takes off. You're located at a viewing platform 2 kilometers away from the launch site. As the rocket thrusts upward, you tilt your binoculars to follow it. Once the rocket is 1.5 kilometers into the air, it is traveling at a rate of 75 kilometers per minute. Find how fast is the distance between you and the rocket changing when the rocket is 1.5 kilometers in the air. So the distance between you and the rocket is this straight line distance, and let's just call that, I don't know, z. And what else is changing? So this distance is changing because the rocket is going up. The height of the rocket is changing. Let's call this y. This distance, the distance between you and the rocket launch site, is 2 kilometers. That is not changing. So we can label that with a 2. Okay, let's see. What do we know and what do we want? So we know the rate, the rocket is launched when it's 1.5 kilometers into the air. It's traveling at a rate of 75 kilometers per minute. So the rate at which the rocket is going up is 75 kilometers per minute. So I could symbolize that as dy dt. dy dt equals 75. And I want how fast the distance between you and the rocket is changing when the rocket is 1.5 kilometers in the air. Okay, so I want dz dt when the rocket is 1.5 kilometers in the air. That's y, when y is 1.5. Okay, so I have drawn my picture. I have symbolized what I know and what I want to know. And now I need to write an equation that relates my important variables y and z. So I'm going to use the Pythagorean theorem again, that 2 squared plus y squared equals z squared. And I can now introduce some rates by taking d dt of both sides. So d dt of 4 plus y squared equals d dt of z squared. And the derivative of 4 is 0. The derivative of y squared is 2y times dy dt. And the derivative of z squared is 2z times dz dt. And now I can plug in what I know and solve for what I want. So I am interested in finding dz dt when y is 1.5. Okay, and I know dy dt. So let's start putting in the things I know. So I've got 2 times y, which is 1.5, times dy dt, which I know is 75. Okay, equals 2 times z. Okay, that's not given. That's not obvious, so I'm not filling it in yet. But dz dt is what I'm looking for. So I'm going to write down dz dt, and I'm going to end up solving for that. But I got to figure out what z is right now. Um, z needs to go right here. and I don't have it written down anywhere. I'm going to have to figure out what it is. So I'm going to draw myself a new picture at the moment in time that I'm interested in. So I've got 2 kilometers. Y is 1.5. What is Z? And I would use the Pythagorean theorem, and I get Z would have to be 2.5. And then I can finish solving this for dz dt. I'm gonna have to do that on a new slide. All right, so I've got my equation. I've put in everything I know. I'm gonna solve for what I want to know, which is dz dt. So 2 times 1.5 times 75. So 2 times 1.5 is 3. 3 times 75 is 225. And then 2 times 2.5 is 5. And then I'm just going to divide both sides by 5. And I get dz dt is 45. And my units for this problem, Z is a distance, so it should be kilometers was my unit for distance. And my time unit in this problem was minutes. Okay, we have a part B, the same setup that we had in part A, but the question is, in terms of radians per second, at what rate are you tilting your binoculars at this time? So here you're looking directly across at the rocket, and as the rocket goes up, this angle that you are holding your binoculars at is increasing. I want to know at what rate is it increasing? So let's label these variables the same as we did before. This is y and z. And what do I know and what do I want? I know the same thing I knew before. Actually, I'm going to write it down here. I still know that dy dt is 75. But this time I want to know something different. I want to know d theta dt, the rate at which that angle is changing. And I want to know it when y is 1.5. So now I need an equation that relates y and theta. Instead of y and z, like in part A, I need an equation that relates y and theta. So here's my theta, here's my y, it's the opposite side from theta. Um, and I'm going to use the 2 instead of the z because the 2 is fixed, and I that makes things simpler. So if I am interested in this angle and I know something about the opposite side and the adjacent side, I can use tangent to relate them. So I'm going to say that the tangent of theta is y over 2. And then to get some rates in here, I'm going to take d dt of both sides. d dt of tan theta equals d dt of 1/2 y. And the derivative of tangent is secant squared theta, and then times the derivative of the inside function, d theta dt. And then d dt of 1/2 y is 1/2, and then times the derivative of the stuff, which is dy dt. And now I have differentiated and I can plug in what I know and solve for what I want. Okay, so the secant of theta, well, I'm going to have to draw a picture in order to help me figure out some of the stuff that I know here. So I'm going to draw a picture at the moment in time I'm interested in, which is 1.5 and 2. There's theta. I don't think I'm going to need the z. So the secant of theta is the reciprocal of cosine, and cosine is adjacent over hypotenuse. Oop, turns out I need the z. Okay, so that turned out to be, that was 2.5 when I did the Pythagorean theorem. Okay, so secant of theta is um, hypotenuse over adjacent, so 2.5 over 2. And I'm going to square that. So I have secant of theta is 2.5 over 2, and I'm squaring that, times d theta dt, which is what I want to know. And that equals 1/2 times dy dt, which I know is 75. And now I can solve for d theta dt. So I'll leave you to do that arithmetic out, but I'll tell you that it comes out to 24. And my units on theta are radians. And my time units in the original problem, the 75 for this distance changing, 75, that was per minute. Okay, so this is radians per minute. But they did ask us to write this in terms of radians per second. So I just have to do a quick conversion. I'm going to multiply 1 minute per 60 seconds. Then my minutes cancel. And I just have to do 24 over 60, which is 0.4 radians per second. You're out superhero watching, standing 1 mile north of the Justice League headquarters at the same height as the helicopter pad on the roof. It's your lucky day, and Superman starts flying due west, taking off from the helipad. If your head turns at zero point 0.2 radians per second when Superman is 2 miles west of headquarters, how fast is Superman flying? Okay, so I'm going to have to do a little work to make a picture for this. So you are standing 1 mile north of the Justice League headquarters at the same height as the helicopter pad on the roof. Okay, so you are 1 mile north. Okay, so here's headquarters. We are 1 mile north. So you are standing 1 mile north of Justice League headquarters, and Superman starts flying due west. So that is from headquarters. He's heading west, which is this way. So let's label this point right here SM for Superman. And I can connect these with a triangle. And I am watching Superman. So Superman starts here and heads here. So this angle is changing, right? My head is turning at zero point 0.2 radians per second, and this is my angle. So I'm going to call this theta. And I know this was 1 mile, and we'll call this distance B and this distance C. So let's see, what do I know and what do I want to know? I know d theta dt, the rate at which my head is turning as I watch Superman is 0 0.2, and that's when B is 2. Okay, so when Superman is 2 miles west of headquarters, d theta dt is zero point 0.2 radians per second. And what do I want? Um, how fast is Superman flying? So that would be dB dt. Okay, at that moment, when he's 2 miles west, when B is 2. So I need an equation that relates theta and B, and I think I'm going to use tangent again because B is the side opposite theta, 1 is the side adjacent, and I'd rather use the 1 than the C because the 1 is static. It's just a little less complicated to use something that's not changing versus something that is changing. So my equation is going to be tangent theta equals B. And then I take d dt of both sides and I get secant squared theta times d theta dt equals dB dt. And now I start plugging in the things that I know and the things that I want to know. And at this point, when I start plugging things in, is when I might need to use the information from the specific moment in time I'm interested in. So that's where I put a 2 instead of the B here. And then I could figure out this third side using the Pythagorean theorem is going to be square root 5. And so at this moment in time, secant theta, again, secant is hypotenuse over adjacent. So it would be root 5 over 1, or just root 5. So I've got root 5 squared times d theta dt, which I know is 0.2, equals dB dt. So dB dt is 5 times zero point 0.2, which is 1. And the units on B are miles, and my time units for this problem was seconds. So 1 mile per second.